Good morning, hello. How is everyone doing? Happy Sunday to you all. I am happy to be back and doing a programming stream. I don't like the weekdays are still gonna be the same. Oh, I can turn that volume down. The weekdays are still gonna be the same. It's still gonna be me doing waking up early and having to go to work instead of programming on with you on Twitch. So I'll probably be doing those afternoon gaming streams unless like something else comes up. But Sundays are still ours, so we're still gonna be doing some programming stuff. I'm sort of playing around with the camera location, which I seem to be slightly see-through. Hold on, let me see if I can fix that. I'm also experimenting with a slightly different OBS configuration here. I'm just capturing the browser and the VS Code setup. So we're gonna see if that works for us. Okay, so what do I want to do? What am I doing? I am going, there you are. Okay, that looks a lot better. Too much. Okay, I think that's much better. There we go. So, where are we? What are we doing? Oh, you know what I didn't put in here that maybe I should. Maybe I do need to do the full screen. I was hoping I could like just do capture one thing since I'm still on only one monitor here. Let me go ahead and minimize all these other windows. And then that way. Okay, so you get to stay up. You can go down. You can stay up. You can go down. You stay up. You minimize. Minimize. And then that way I can just switch over and show the full screen, because I realized that the Notion document would be nice to put the notes into too. I have like sort of want to test not putting things into Notion potentially and like storing them in the full repo, which might be helpful, or like then just having only two things showing on a screen. But we'll get to that later. Okay, so all right, all of you are good. Let's try. Let me add a new scene. This will be like full desktop. And that will be main. Let's try this. And I believe that should be the full screen. Maybe. I'm watching the preview of the stream, which is on yeah, there we go. It's on a significant delay. Even though I've turned the delay thing off. So, maybe it's turned back on. I need to double check my Twitch settings, I guess. All right, so I think we're ready to go again. We can take a look at our Notion document. We've got Mem manual drop look like it's coming up next. The other thing I've been thinking of while going through this entire thing is if I wanted to make a course around like just the Rust standard library, that would sort of like, I don't want to compete with the book, but necessarily. So what would I probably do? I think it would be like a supplement to the book. Something that you can like, okay, you go through the book, now also like you can go through this if you want something else. There are plenty of those things too, but I think that there's less less things that like people know where to go after the book is done. Okay, so manually drop. We're gonna go take a look at that next. So let's do that here. And I realized I probably could organize this a little bit better. I'm thinking that like if I do a course or I go through this again, but in more thought process, I'll probably use a better folder structure. Maybe not just examples. I'm not sure. Like there's a lot of different things that I might do differently if I'm starting over again. But until then, we're just gonna stay with the flat for right now. So this is gonna be manually drop. It's a struct. All right, so what do we got here? A wrapper to inhibit compiler from automatically calling T's to structure. This wrapper is 0 cost. Oh, so it's literally something we can like wrap around some things. That way we have to drop it and nobody else does. Manually drop is subjected to the same layout optimizations as T. Okay, so like whatever we pass in. As a consequence, it has no effect on the assumptions that the compiler makes about its contents. For example, initializing and manually drop with mem zeroed is undefined behavior. If you need to handle uninitialized data, use maybe uninit instead. Maybe uninit. I don't think we've seen that one yet. But we'll add it to the queue. Note that accessing the value inside a manually drop is safe. This means that a manually drop whose content has been dropped must not be exposed through a public safe API. So accessing the value inside a manually drop is safe. Well, wait a second. It's safe, but also don't do it. Are you saying that I can't do it even if I want to, or are you saying that it's safe to do so because you will handle it for us? Aha. Correspondingly, manually drop is unsafe. Once I tell it that it's dropped, I can't access the value inside anymore. Rust has a well-defined drop order of values. To make sure that fields or locals are dropped in a specific order, reorder the declaration such that the implicit drop order is the correct one. So, like manually handling this memory-wise. It is possible to use manually drop to control the drop order, but this requires unsafe code that's hard to do correctly in the presence of unwinding. For example, if you want to make sure that a specific field is dropped after the others, make it the last field of a struct. Okay, so context will be the last one dropped. Interesting. Okay, I had heard of this before, but it's nice to actually see it implemented in here, which is when you drop, like when something gets dropped, the order of the fields is important here. The top ones get dropped first, the bottom ones last. So it depends upon where they are added in the struct. And I guess that's a way that we don't. Yeah, Rust guarantees that fields are dropped in order of declaration. It's kind of important there. Okay, so we have implementations. So manually drop, wrap a value to be manually dropped. So there's not really much here to use. Like these are just different structs. So we have new. So let's play around with this a little bit before we write like all. Well, we could note them down first, but we'll play with them before we like fill out the information. So patients. So we have new, obviously. Into inner. Take. Drop, okay. And we have the trait implementations. So these are all the traits that it implements. Okay, so it's clone, debug, default, deref, deref mute. Okay, so hash, so we can throw it into a hash map. Order, so it can be ordered when it's inside of like an array or something. Partial equal, partial order. Oh, you can compare them against each other. That's actually really interesting that it handles those things. I'm guessing that it does them as long as T implements them too. All right, let's play with it. So let's say we've been using our location struct. Let's continue doing that. So we're gonna have a struct location with an X and a Y. All right, so if I want to use this and throw this into a manually dropped, you're going to be equal to a manually drop new location. Let's do like 10.0 and 20.0. Okay, so that gives us our thing. Can we, like, what can we do with this? Like, when would things normally get manually dropped? If they go out of scope is one thing. So if I hand something to a function, that would normally drop it. So let's say I have like another function. So maybe this derives debug, and I want to create a logit function that's going to take something. So it's going to take like a T, where T implements debug. And then so you are going to be like the thing, right? So the thing to log, and you are my T. And we're just going to do a debug uh, and if I call that then, so I do log it and pass it in the manually dropped location. Now this should work just fine, like as we wrote right now, because we're not doing anything where we're like now trying to use it. But it should, like I would expect that it normally gets dropped at the end of this block here. So I shouldn't be able to like debug again. So like if I try to debug again, hey, let's say I just try to log it twice. Use of move value. Now, I guess it's not the drop that's getting us here. It's the borrow checker. So we've given ownership of it, which means we don't have access to it anymore. So what way, like how could we drop something without moving it? Let's look at their examples here. So you have, they do a manually drop and they throw a string inside of it. You can just do stuff on the string because it implements deref. But drop will not be run here. So it's not dropped, it's just owned. Into inner extracts the value from the manually drop container. This allows the value to be dropped again, but once again, we've given ownership of it. So that's not really helpful. Can I do the deref when I'm passing it in? You might be right, KJH. I wonder if that's the thing. Can I deref you? Move out of dereference. Move occurs because value has type location, which does not implement. Okay, if I want that, how about the into inner? Can I do that? What was it? Oh, it's a const function. Oh, okay, so hold on. So it's not that. I'm gonna do a manually drop into inner and then pass it the manually dropped location. Use of the moved value. So you don't like this. You take ownership of it, don't you? Or maybe if you want to keep a file open or something, I guess, maybe. You had a situation where context had a drop handler, which should only run if the context was passed to the application, but as long as it was within library runtime, its drop handler should never be called. This could be solved with manually drop and its into inner just before passing the context to the application. I guess that makes sense. Yeah, you want to keep it and like you want to make sure that it can't get dropped by accident. But it does feel like KJH is right that it's mostly going to be useful for like unsafe, like other code, like FFIs. But yeah, it's hard for me to like sort of imagine when I want to use this. Knowing that it exists is interesting. Now this is interesting. Okay, so there's this unsafe take that allows us to take something out, but then it's our job to make sure that this manually drop is not used again. So does that mean I can actually do this? So like, let's try, let's see, what are you? You're not a self. Okay, so I can just maybe do a take here. You're gonna yell at us because you're unsafe. So what if I do an unsafe block and throw you in here? Mismatch types expected immutable reference. Okay, so you're certainly gonna make me be immutable here. It's not complaining. Yeah, that works just fine. So our first debug is the location, so I take the thing out and then I can take it again. So we can do some evil stuff in here. So I can use this manual drop twice. The contract says that I must not. But that's up to me, the silly developer who may do unsafe things. So that's certainly interesting. So I suppose if you really want to get around the borrow checker, you could just do this. It's a terrible idea. But what are you actually giving me? When I do the take, yeah, look at that. It's the full location. It's not a reference to it. It's the full location and you're not getting manual drop. Okay. Now into inner, I guess that might be the other thing too, is I was dropping manual drop, not dropping the thing inside of it. If I do the into inner and I hand it, okay, you can't, okay, found a mutable, so it can't be a mutable reference here. So that's our big difference between take and into inner. Take leaves manual drop alone. Into inner consumes the manual drop, which therefore is essentially like consuming this, the thing that I put into the manual drop. So new, this is instructor into inner is interesting. So this consumes the manual drop and returns the I guess like it returns the contained item. Bear Duda, hello. How are you doing today? This consumes the manual drop. Oh, I already said that. Okay. You're existing? Well, that's good, I guess. Take is more interesting here. So take is more dangerous. Oh, you redeemed Pet the Cat. I will keep that there in case he comes down. Zilby was upstairs hanging out with my wife, but we're gonna be here for a while. So if he does come down, I will definitely pet him. I rearranged the room and I changed my green screen behind me so it's no longer like in the middle of the room and looming around. He's been willing to come here more often. So there is that. Okay, so take is super interesting. So And also this is like a static function. So like static method on the manual drop struct. Okay, this is static method on the manual drop struct that takes a mutable reference to an instance of a manual drop and returns what it contains without changing, like without removing. So without touching, no, it clearly touches it, without dropping or taking ownership of the contained item. So like this is like the super scary sort of like thing that you can do is this. We can have our manually dropped location. We can then run a little bit of unsafe code to take this out. Now I wonder, can I do something crazy like this? Like let location is equal to this unsafe. I think I can. So then we can do another logit here with location. Let's not do that here. I have semicolons, don't I? Save. Okay, there we go. Yeah, so take a look at this. These, like this location is exactly the same thing that's inside of here. That's really interesting. I wonder if I can do the memory thing. I think I can. I think I can do a print line. What was it again? It was like colon P for pointer. And we're gonna give it location. So let's not do these. And then I want you. Okay, we have the location, and I want the thing inside of manually dropped, which in this case we can do the into inner, I believe. So we can do a manually dropped into inner. We'll take the manually dropped location. That takes ownership of it, but in this specific case, it's gonna be fine. Maybe, possibly. I have to do like a reference to it, right? So if I run you, no, they're not the same locations. Okay, so they're not exactly the same. Interesting. But they're not really clones. Is it a bitwise copy? Can I somehow mutate you? Can I make you mutable? And then mutate you after this location? So can I do like location.x plus equals 10? So now we would expect it to be 2020. Yeah, let's see if it was like a bitwise copy. Use of move value location. Okay, so we moved this here. Hold on, let's do you this here first. And let's see if this works now. Yeah, okay. I think you're right, KJH. We're copying it out. So we're not getting like a reference to it. So this is not exactly the same as like read or what was the other pointer thing that we sort of did? It's not the same as that. This is giving us just like a new copy of the thing. So we change it. This location is exactly, do this here. This location is like a copy. A copy of the, it's a copy of like the location stored inside the manually drop. However, it is not pointing to the same place in memory. Take seems to use pointer read internally if you look at the source code. Oh, really? We can take a look at that. Oh yeah, it does. Use pointer read with the, okay, so. We are reading from a reference, which is guaranteed to be valid for the reads. Okay, that makes sense. Yep. So I thought that read gives us something that, like a piece of memory that's actually the same. But I guess it's not? I think, well, and also like if you consume and drop something, it drops the other thing too. So there's maybe weirdness in that? I don't know. But so it's a copy. So we managed to create a full copy of this. So changing this won't change the location inside the manually dropped instance. So then this would be x is 20.0, y is 20.0, and you are x is 10.0, y is 20.0. However, we can like copy this as many times as we want, even though we don't implement copy. Pointer read also copies, but if you copy a smart pointer, they point to the same thing. That's what it was. I was copying a smart pointer. That makes more sense. All right, so I mean, clearly a little bit dangerous, but not as dangerous as some of the stuff we've looked through already. It's now I can definitely see at the end of this, because it manually drops, it's oh, Urbanovsky, I don't have a commands of, wait, I do have a commands available, but it like takes you to that other page. I don't have somebody to like put something in there, which would be nice. Also, hello, good morning. Let's see. So yeah, this is interesting. This function runs, okay, so drop. So manually drops the contained value. This is equivalent to calling it pointer drop in place. Ooh, pointer drop in place. We haven't looked at that yet either. With a pointer to the contained value. As such, unless the contained value is a packed struct, the destructor will be called in place without moving the value and thus can be used to safely drop pinned data. If you have ownership of the value, you can use manually drop into inner instead. So if I don't have if I don't have ownership of it. So I have given ownership to this manually dropped locate to log it. So I no longer own this manually dropped, which means I need to run drop myself. So can I do that? That's going to be a manually drop, and then a mutable reference to the manually dropped location. What? Let me do. Oh, this is gonna yell at me saying it needs to be unsafe. Can you do that for me? No. But I can't do that because it's moved. I don't have ownership of it. I guess because it's been given away, I can't do it because it, like, I don't own it anymore. But what they're talking about is not the fact that I have this thing. They're talking about if I pass in like a reference to this T here. So if I do something like this, now I can do this because I do own. So we own manually drop, so we can call the drop static method and so drop the contained item in place. This function runs the destructor of the contained value. Other than changes made by the destructor itself, the memory is left unchanged. And so far as the compiler is concerned, still holds a bit pattern which is valid for the type T. However, the zombie value should not be exposed to safe code, and this function should not be called more than once. To use a value after it's been dropped or drop a value multiple times can cause undefined behavior, depending upon what drop does. This is normally prevented by the type system, but users who manually drop must uphold these guarantees without assistance from the compiler. So if you use the reference as an argument, the variable is not moved. Yeah, exactly. So I guess the way I think about it is it's like an owner, like we use the ownership system as a metaphor. It kind of works here. I am loaning this location to logit. So logit is taking like a borrow, so it's borrowing it. and therefore it can use it, but it doesn't have ownership of it. It just temporarily has it. Really, it just has this like reference to it, right? And then I did the same thing again with the manually drop instance, and it doesn't take ownership of it. It just borrows it for just a little bit of time. And it's like it breaks down a little bit when, you know, in real life, if I take my mug of tea and I loan it to somebody, I don't have access to it anymore. But in this case, I do have access to it because I'm just loaning a reference to it. So I'm really just saying, hey, if you want to come over here and drink this tea, you can. Here, it's like sitting right here, and I promise it's not going to move. And somebody else can say, okay, I'll come and drink this tea. And then they do. And then so can I at the same time. It's weird. I could pass a lifetime, or the compiler automatically figures out what that lifetime is going to be and inserts that for us, which is kind of what's happening behind the scene, which is why we don't need a lifetime here. It knows that this location is going to live until the end of this block. However, if I call drop, apparently what happens is it doesn't remove the item. So it's not going to actually drop it from memory. So it's going to call the drop method. Of the contained item, but then leave the item sitting in memory. So I guess this could be good for like FFI users. If you need to drop it, but you need like the C or C++ to still be able to access that memory, you want to keep the memory for some reason, this gives you that, I guess. I don't know. I haven't done enough FFI stuff to like know how that would work. But let's impl drop for location here. We haven't done this. We should actually add in. We should definitely add in drop. The trait drop. What are you? You're ops drop or? Oh, yeah, ops drop. Okay. So normally this is not this is not manually code to remove things from memory. It's just like, hey, I want to do stuff before it like gets dropped. So for example, we can do a debug here of I am being dropped. My values are actually, let's do this as a print line. My values are X, Y, like that. And then I can do self.x, self.y. So if I run this drop, we should see that message come out here. And we do. Okay, so look at this. It comes out twice. I am being dropped, my values are x10, y20, and then I am being dropped, my values are x20, y20. So what happened here? If you remember, we have two copies of the exact same thing because we did this take here. So we have this location at this time, so we're borrowing it here. At this time, location drops and gets removed from memory. So therefore, the drop runs. And then the other one is we call this drop, which then runs the drop. So This is the manually dropped location, drops, but does not get removed from memory. Now the program ends here and then everything gets freed. So what we've done is we purposely created a memory leak. Now they say, whatever you do, do not run drop twice. So let's go ahead and run manually drop twice. Now in this specific case, I don't think it's gonna have any effect on us. Although notice that drop gives us a mutable reference to self. So I wonder if I can do some really weird, crazy stuff with that. Like mutate yourself so that way each time we drop, instead of dropping, we just, you know, get something more. But I don't think I can access this anymore, but maybe we can. Let's sort of like experiment with this. So if I run this twice, we're now gonna get 3 drops, I think. Here's our 2 drops, and then here's our other location that got dropped. Okay. Now, what if inside of location, I also do something a little bit weird, a little bit terrible, and I do self.x plus equals to like 1.0, self.y plus equals 1.0. I don't know, just because I can. And then if we run this, so it's the same place in memory that's being incremented. Now, after I drop this twice, I know I'm not supposed to do this again, but can I actually get, can I take it again? So like, can I do this again? It's like, let another location equal to you, and we're gonna do a manually drop take, and throw in this it's a mutable reference. We're gonna return that and semicolon u. I can indeed. So, oh my gosh, this is like the worst stuff you could possibly do. So we could do another logit with another location. I guess you're a reference here. And yeah, we dropped it twice, and yet we're still using it. So manually drop doesn't allow you to get away from the borrow system, but it does allow you to play with memory in really weird ways. That's actually pretty cool. So drop is going to runs the. This is not merely a double free; it's a quad free. Yay! Yay! And you know what's funny is that it's not a free at all, because we haven't freed any memory. Like, that memory is still there and it's still valid. But I don't think so there's no ways for me to extract anything from here without taking it. Like, without taking ownership of the thing and having it like remove the thing inside of it. Because if I do the into inner, that does a true drop inside. And it's no longer available to me. That's okay, that's interesting. All right, what was I doing? Okay, so runs the drop trait method. on the contained item without removing that item from the system memory. This does mean that drop can be run multiple times, but should not be due to or at least you should be very extremely careful. Like what we're doing is not that bad, right? Because I'm not like changing something. Does not mean that drop can be multiple times, but should not be due to what drop may or may not be doing. Now, I suppose if we want to be extremely dangerous, if I don't implement drop myself, the system drop is going to implement. And the system drop does actually, I think, remove it from memory. If I'm, or like it reinitializes it, I think so. So what happens now if I run this? I feel like I'm getting there's no other weirdness. Let's see. I log it, drop, take it, and then log it again. So the three logits happen. So it's not okay. So the normal drop just I don't know what it does. I don't know what the default drop is. Maybe there's not a default drop. Is there a default drop? No, okay, so there's no destructor normally. Okay. I think there's no destructor normally, so it's not going to free the data. So drop doesn't actually free the data by default. That happens when it goes out of scope. So if you want to be evil and you want to like throw this type of stuff in here, and you're working with somebody who doesn't have advanced knowledge of Rust, they may, like, you might be able to throw these type of things in different files, like far away from each other, and that could potentially, like, it will be legal, and Clippy is not upset at this. Can I set Clippy for maximum? Let's see. Where's my Rust analyzer? Let's see. Clippy? Oh, there's nothing. Fine. Isn't there a way to tell Rust analyzer Clippy, like, use everything? Be extremely strict. Okay, cargo command to use for cargo check. Oh, I forgot what that is. Hold on. So, oh, I don't have. Is it like cargo Clippy? Oh, what is it? I think I have Clippy installed. I may need to. Maybe I didn't. Also, hello, Sureshock. Maybe I didn't. Maybe I did do. Wait, isn't it a rest up thing or is it a clippy? It's cargo clippy. Okay. I want the most strict version. To allow or deny Lint. No, what's the one that's like the most strict? It's like cargo. Cargo clippy dash F, I think. Or not. Oh, there's dash dash help. No, that's exactly the same thing. Hold on. Clippy, cargo rest. What else am I searching for? It's like the most extreme, so like check, strict maybe.
Yo, what's going on?
The strictest work. How to configure to be clippy as annoying as possible. Enable clippy all. Clippy all. Okay. Wait, is that in a cargo toml? Add this to the beginning of a crate. Oh, cargo clippy dash dash all. Okay, I think that's what it is. It should be dash dash enable hard mode. Wait, is that what it is? Okay, let's try this again. Cargo clippy dash dash enable hard mode. No, it doesn't like that. Can I put this in here? Doesn't seem to care about this stuff. Do you put that in code? Oh. Oh, it was just a joke. Oh man, I was hoping that was real. That would have been so nice. Ah, that's too bad. Where was this? I lost my clippy. I think it was cargo check.
Yo, what's going on?
Wait. Let's stand with. There it is. That would have been nice. Okay, so warn clippy all, something like that. Okay, so I'll leave you the same here. We're gonna come back to you. And we're gonna throw up here warn clippy all. I think it's the hash, right?
What's going on?
I can type. Oh, come on. Hold that shift button down. Useless lint attribute. Okay, I have to do this on maybe the everything else. Let's put it on main. You don't care. So Clippy's fine with this? Oh, you can enable global lint using the bang symbol. Oh, okay, that's what that was. It didn't like that for some, well, at least Rust Analyzer didn't like that. If I tried to do something like this, can I do like bang here? Probably makes it a comment. Yeah, it doesn't like that. I'll have to play around with this. Okay, so it really is a shebang. It's basically a shebang. Okay, and Clippy is perfectly fine with this. So that's good to know. That is interesting. That, yeah, just drop as many times as you want. Clippy doesn't care. Clippy's fine with this. This is fine. Okay, so knowing this, like obviously we could do some evil stuff in this drop here. I don't exactly know what we would do to make it super easy. I guess when you're on unsafe zone, they don't care. I guess so. Clippy may or may not be checking that. I haven't looked into like Clippy too much to like know what exactly, like how exactly it works. But we can do crazy weird stuff like this. And then the location in memory, and then I just take it again. And this all works. So like, yes, we can take it again, even after running drop. Love this quote from This Week in Rust. Clippy is for people who find certain emptiness inside when they finally get code through the compiler. I think I like Clippy because it forces me to be better. So I guess I have that kind of emptiness. Okay, so we have this working. Yay. Okay, so I'm gonna throw this in here. All right, so we have our drop. This does mean the drop can be used, but should not be. Okay, so then let's also note that into inner is not unsafe, but take and drop are both unsafe. Which means I can change their color to, let's make it like a nice red. Oh, try this. Deny Clippy pedantic. Let's do that. Okay, so this is gonna be deny Clippy pedantic. And just to make sure, let's go ahead and restart Rust Analyzer. Make sure it's not something like Rust Analyzer isn't seeing it. No, it's even at its most pedantic, Clippy is fine with this. It's fine. We'll just sort of leave that there. All right, so that's manually drop. Manly drop is actually kind of fascinating. We can do some like crazy stuff with it that I probably won't be using. Like I don't know any legitimate uses for this yet, but I've myself not done too much like systems level programming. Most of my stuff with Rust has been higher level programming, like game development, web server type stuff. I haven't needed to do anything tricky with memory management yet. The ECS is probably the closest thing that I've come to it, but I've there might be some interesting things that we can do. Like we might be able to do some things like with take and yeah, but not really. Can't do that because we can't get we can't get immutable reference to it. So we'll have to deal with that later. For now, let's just mark this as done. By the way, turn on both Lint so that, oh yeah, we could try that. So it's, go back to Warn again. We'll have Clippy Pedantic and Clippy All. Did I see a Clippy Absurd in there? Absurd extreme comparisons. I guess absurd isn't real. This would be great if absurd comparisons is interesting, but absurd would have been great. Maybe that could replace pedantic. But yeah, this is fine. It's fine. Everything is great. I need to do another. Okay, so this is manually drop struct. All right. I'll go ahead and push that up at the end. I mean, subtraction, absurd extreme comparison is probably like you can't do minus in function named sum. Oh, minus means subtract. Yeah, I figured that. That's interesting. Some of those things like that Clippy protects you from, I haven't even considered ever even trying to do because I'm not like that evil of a person. All right. Memory transmute. Okay, so transmute. What I'm gonna do is I go into the examples here. I found like a cool thing that I can do to sort of like set things up is I can do code transmute, and then it opens up here. If I do this like in VS Code running in my system, sometimes it works, sometimes it like opens up a new code instance. But here, because I'm in code spaces, it seems to work every time the way I expect it to. What I don't know how to do is close this window without having to go back to it. So I have to like do a twice thing, which it's not that great. Okay, let's head back over here. So we have our Mem Transmute. It says that it checks for comparison with min-max value of a type. Oh, so, min-max value of a type. Interesting. Heck, maybe someday we can do like a Clippy deep dive, like into the lints, like not necessarily like how Clippy runs, but like the lints themselves, and like understanding that and maybe building out our like perfect thing. But that's a little bit interesting. All right, let's go take a look at Mem Transmute. That's the wrong one. No, this is the right one. I want back to here. Transmute. Okay, this is a function. And is that correct? Wait, wrong one. It is a function. Unsafe again. So reinterprets the bits of a value of one type as another type. Okay, so like x is greater than I32 max, which is always false. Oh, right, because it can't be. Yeah, because that makes sense. It can never be greater than that because it would have buffer overflowed. Both types must have the same size. Neither the original nor the result may be an invalid value. Transmute is semantically equivalent to a bitwise move of one type into another. It copies the bits from the source value into the destination value, then forgets the original. It's equivalent to C's mem copy under the hood, just like transmute copy. Because transmute is a by value operation, alignment of the transmuted values themselves is not a concern. So what this is telling me, Mem Transmute is one of those things which gets people on the forum to get a little twitchy if you ask about it. I mean, I figured like a lot of stuff that I'm doing with this memory stuff and like unsafe is gonna be one of those things that like cause people like, what are you doing? No, don't do that. Stop. Transmute is incredibly unsafe. Okay, so now this says it must both types must have the same size. So my guess from reading that is that if I try to convert an F32 to any other type, like a U32, then it won't work because they don't have the same size. Like the word must in the documentation is super interesting to me because sometimes they use the word must as in the compiler will stop you. And sometimes they use the word must as in you, the developer, must not do it or else bad things will happen, but we're going to go ahead and let you do it because unsafe. So let's try it. So if I have an F32, so we have I don't know, like we have a size that's an F32 and you're gonna be equal to like 10.0. Wait, does F32 and U32 have the same size? How do I check the sizes? You can do things like convert BHDR0 to F32 using transmute. Oh, standard mem size of val. I think you're right. That's what it is. So if I can do a debug standard mem size of val, and then it's a reference of like size here. So if I do that and we run you're 4, okay? Now, if I do let maybe like health, let's actually just name this like F32. And you're, I probably shouldn't do that. F32, let U32. You're a U32. It's equal to 10. So otherwise you're the same. Standard mem size of val reference to you are F32, and you're gonna be this U32. What are you? You're right, you're both 4. Limacode, hello! Good morning. Well, I guess morning for me. I think it's afternoon for you, or is it evening? I can't remember. Oh, and Lumicode, thank you so much for the subscription. And you're on a 3-month streak too. Thank you so much. Glorious third of an umbilical cord. 6 months more. And then we'll have that Twitch baby. Okay, so. You are the same size. That is correct. Oh, mem size of? Oh yeah, I think I can do that too. So that's like what this value is. We can get that. So we can do a debug standard mem size of F32. Let's try this. Yeah, so you can see that you're 4. So here, let's try to make this create like a size of thing here for us. So like print size of type. And do a T. I don't care what that is. And we're just gonna do debug standard mem size of type. So that way I can instead, all right, let's just like print these out and sort of like take a look at what we've got. So we've got print size of type. And let's do U30. Okay, so we already did like U32. And you could be an F32. Now we could also do F64. And can I do a U64? Yeah, there's a 64-bit U. Let's run this. Okay, so 4488. So if I do F64, so a F64 to F32 should not work, but a U32 to an F32 and back should work. Now, how about the eyes? If I add in like an I32, that's also a 4. Okay, so all of the 32-bit are 4 bits. All of the no, it has to be 32 bits. It takes 4 bytes. Is that right? Due to Unicode, I think char is also 32. Let's try it. A char is 4. So yeah, that is a, oh, so yeah. But that makes sense because a char is really made up of a bunch of U32s in like a vector. If I really want to like split out like a string into like the characters and then put them in like binary, that would be U32s. Divide anything by 8 gives the size in bytes. And 8 is like the number of bits in a byte. So that makes sense. Makes total sense. Okay. So given this information, we can now do some interesting things using this transmute. So before we read it, I believe that it said this is incredibly dangerous, so it's probably going to yell at us about using unsafe, because this function is incredibly unsafe. Heck, it links to the Nomicon. That's how unsafe it is. So standard memory transmute, and you take in 2 types and you turn into the U. Wait, two things. No, okay. So it takes in two things here. But I transfer. Okay, so it's gonna be some turbofish stuff. So let's see. If I want to do a let's see, like my let results is gonna be equal to a transmute. I have to give it the first type. So we're gonna say we're gonna go from like F32 to a U32, and then I have to give it an F32, so like 100.0, and you're gonna return to me a U32. But if I have like the .0 is gonna be easy. That's not that bad. Now you're also gonna yell at me because you need to be unsafe. Yeah, we're gonna close you here. And then we can just debug result. Now, this should be pretty easy for it, right? It's just gonna be 100. We're not gonna lose any data. Yeah, Clippy is unhappy with this because transmute float to int, we're losing data, right? We're gonna lose this dot here. But it's gonna let us do it. And yeah, data's some garbage. This is some garbage here. That's interesting. What are you? IEEE 754 magic. Yay! You think it can infer? You think it can infer. So if I do this, but then I have to say that you're gonna be a type U32. And you have to be a F32. Okay, yeah, that works. It does need to know each of the types. Then it can infer. But that's super interesting. Like, what is this? Is it just garbage from memory? Yes, correct, because float is some mantissa and some other things. I guess like float includes. It's the representation of 100 in U32. Really? Because if I do like, I don't think if I just do like -1, now we're gonna get this like to 5. Yeah, so it is that a larger number even? Ten characters or 10 digits. Okay, yeah, no, it's exactly the same. Try transmute again and you will see. Okay, what should I transmute? Should I transmute back? That could be interesting. We could transmute back. So like let back again. So you're now going to be an F32. And we're going to give it result. Okay, so the clone should work here because it does a copy. So let's do this. Yeah, okay. So that is interesting. What? So in bitwise, it's storing the dot somewhere inside of it. The interesting thing is like it's such a different number that I wasn't expecting to see that. Or is that just garbage data from memory? You can look up IEEE 754. Oh yeah, let's take a look at that. IEEE 754. Okay, so floating point arithmetic. Okay. Now, where am I looking in here? I don't want to necessarily have to read this all out slowly. We have the formats. Okay, in representation encoding memory. Some numbers may have several possible exponential format representations. If b equals 10 and p equals 7, then negative 12.345 can be represented as negative 12.345 times 10 to the negative third. Wait, is that what's happening? Oh, sure shock. I'm so sorry. Float converter. There's this talks about it too. It looks like, oh, you went to, okay, you're on a different site. So you go take a look at that one. Oh, this is interesting. Okay, so we have, okay, so this is JavaScript, but it's probably the same. I think that's F64, right? So if we entered in something like 100.0, value store actually stored in a float is 100. The binary representation is this. There's a hexadecimal. Okay, so that's what's going on. Now, that's the Manta says 4718592. If we look at you, it's not exactly the same here, but it might be doing it different. Oh, it's F32s. Hold on, let's do F64s. That will make it the same. So U64 to F64. That might be more consistent with what we're seeing then. That's a nice long number. So if we move over here, I don't see like the 47 unless that's rounded. No, it's not. But it is interesting the way it's storing that. Cloud proceeds to explode as I click run. I know, except it allows me to do that, so it's perfectly fine with me. Like, Rust is happy with me doing this. It's just like, Clippy is like having a conniption. So I can definitely store these things, and then I can do some weird stuff. Like I can do stuff like, okay, Give me this result. Make it mutable. So what if because we know if we put it back again, we get the thing back, right? Like this 100.0. What if I just add 1 to this? So if I say result plus equals 1. And then I put it back into the F64. Okay. The 1 at the very end corresponds to the maximum number of decimal points plus 1, I think. So that's what we're getting here is like some... I think if we go back to the Wikipedia page, it's a little bit easier to see, is we're storing this in memory like, where was it? Like this. If b equals 10 and p equals 7, then negative 12.345 can be represented as negative 1, 2, 3, 4, 5 times 10 to the negative third. So we're doing like a positive number, which then would just be no negative. It's stored as like this big thing times, and I think it's storing like the 10 to the negative fourth part as like a number inside of that. So it's then turning that whatever, it can read that again and then convert it back over. I don't think I'm explaining this correctly. But somewhere in here is like there's a representation here saying, hey, at this point, then you're going to be like the number of things multiplying by. Float is represented as a sign to the exponent and mantissa. When you transmute it, uses those bits to reinterpret as U64. Now, the end result is, when would I ever do this? Probably not. I don't understand why I would ever want to do that. Once it's here, it doesn't know that it's a F64 anymore. So as does it safely, Transmute just lets me see what it is represented in U64 format. One good example of Transmute is creating window objects in Rust. Oh, really? Are you talking about like actual window objects or just anything working with the graphics card? Windows objects? I have not worked with the Windows library. It's something I actually want to do because there's some cool things I think we can do with that. Windows like press yes or no. Oh, interesting. Interesting, okay. But we can go back and forth between a lot of this stuff. Now, this is a really large number. So if we go back to U32, and that way we have a char again. And so let's say we have this transmute. I don't want to go into U32. I want to go into a char. Don't want to add 1 to you. I don't want to go back. I just want to debug what this result is. Like, what is the char of a 100? I think this is going to be not good. I wonder if it's going to crash out of range of what a character could be. I mean, it gives me that, but I don't know what that is. Certainly the terminal can't display that. The famous inverse square root algorithm from Quake using floating point bit hacks, but floating point hacks can be done without transmute. Okay. Yeah, I've heard about Quake doing some really interesting math stuff. Like, be able to get what they did in like the speed at which they worked at too. but it's interesting. So I can go do all these different things, and I'm doing it. I'm getting like the actual memory values. Now, what if I did like 100 U32, and I'm going into a char? Okay, that makes more sense. So now this is D, which I think is the 100 Unicode. Unicode, is there just like a list of them? Okay, so small letter D, there it is. So you 100 right there is the decimal. So it's the decimal version of this. So I can get that way otherwise, but I think I can do that with an as too, right? Oh, Sure Shock, you have a good example of transmute. Let's go take a look at that. Okay, so FFI. So we have this H module and farproc. Okay, they're going to be constant C voids, which I don't know what C voids are, but that's part of the FFI library. Okay, so standard call, load library, A. Okay, process. Okay, so where are we doing transmute? Right here. Get procedural address. This H, which is load library A. Okay, so load a library, a DLL, as a pointer. So get that as a pointer, and then transmute that from that to message box A as pointer. Oh no, that gives us a procedural address. Then we transmute that into a message box, and then we can then display that out. Interesting, okay. C void is just, okay, so like no op essentially, just like nothing. That would be sort of like bang then, right? Right? Like the equivalent to that, like just doesn't return anything. Okay. That is interesting. I think, well, I do want to play with some like Windows programming. I have some like ideas of like projects we could do, which could be really fascinating. But this is probably gonna have to wait for us. Like Transmute is probably gonna have to wait until we do some, we're like forced into learning this. So I think what I'm going to do is on hold until I learn this stuff. So we have, no, don't do that. Okay, so we have futures, we have the question mark, and then here, it's from the Faster Than Lime blog. Yeah, that could be interesting. I have like so little time to like follow everything. There's just so much to look at. It's interesting. I will add that to my reading list, but I haven't read very many blogs recently, so I don't know if I'm gonna be able to get to them. But let's do like Windows programming. Too little time, too many things to learn. I know it's like so much cool stuff. So I'm gonna throw this down here. We're gonna revisit it later if we sort of like get there. I'm guessing that some of these may be in that same sort of like grouping for us. So if we do maybe uninit. What is maybe uninit? Also for you, we played around with you, but we're not going to do anything yet. Maybe to like keep it easy for us, I'm just going to use graphical for now. Let's just do transmute will come later. Let's add in file. What is that? Maybe uninit. Okay, so given that, head back over here. Maybe uninit. All right, a wrapper type to construct uninitialized instances of T. Okay, so the compiler in general assumes that a variable is properly initialized according to the requirements of the variable's type. For example, a variable of reference type must be aligned and not null. This is an invariant that must always be upheld even in unsafe code. As a consequence, zero initializing a variable of reference type causes instantaneous undefined behavior, no matter whether that reference ever gets used to access memory. So we can do this mem zeroed. So I kind of want to add that in. Do I have a zeroed? I do, mem zeroed, okay. So that gives us, okay, undefined behavior. Maybe uninit is also in the Faster Than Lime blog where he uses maybe uninit to create buffers because some Windows 10 API requires you to pass buffer before calling the API. Oh, really? Interesting. So you hand it an uninitialized buffer and then you call the API, which then initializes and fills it out. I think I read that somewhere else that like this is mostly for FFI stuff where you need to be able to like hand it unnecessary stuff. The other thing is going to initialize it for us, but we have to like prepare things around. And you can call assume init later after the API is called, right? Which of course like assumes that the thing that you're using is good and like true and like working properly, which we're about to violate. Ooh, hello, hi. We have a Zilby here. Lord Kitty has arrived. Do you want to hang out with me a little bit? Maybe? No? You're just here to say hi and then leave? I don't. Okay, so I haven't set up my second monitor. Kitty is big now. I know. He got big. He's a year and a quarter old, I think now. Yeah, he's like almost at his adult. I think he's at his adult. And I have that camera somewhere. Where did I put it? Oh, it's in a drawer over there. I need to reset it up. Because like my entire streaming room has gotten sort of like reset because I wanted him to actually come down here, which he does now. And he is. Oh, I have a heater on over there, and he's very concerned about this thing that's sort of like rotating back and forth and spewing out hot air. He's very concerned about it. Oh, and are you leaving now? Bye, Zilby. It was nice seeing you. So I mean, we gotta pet the cat in, but it's like so small. I'm so sorry. Yeah, I can understand when they can eat some. So I have not tried the cucumber thing with him. I feel like it's just too mean to like do that to try to make him too afraid of stuff. He's already like gets scared so easily by a lot of things that I don't want to just like do that on purpose to him. I feel that that's just mean. Maybe if I can like help him get his mojo, as Jackson Galaxy says, maybe then I can do some of that kind of stuff with him. But until then, it's funny but evil. Like when he's a confident cat, maybe we'll do some interesting things like that. Okay, so what are we doing? We're gonna do some evil initialized stuff. So we're going to zero out some memory. Let's throw this over here and let's put you on the right. So we're going to start by creating let's do the same thing they're doing here. We're going to create an I32 and it's going to be zeroed out. So we're going to say like let this X is going to be, it has to be unsafe. Mem 0. Okay. Now if I do that, you don't know what you are, right? Okay, we need to give it a type. So let's give you, now you're giving it a reference to I32. Can I just do I32? I can. Okay, perfect. Now they say be extremely careful with this because this is like unknown. It's like instantaneously unsafe and undefined behavior. So clearly we should debug this. Clearly, the only answer. It's also like why I'm happy I'm doing this in code spaces, because if I'm gonna take down a system, let's take down a VM that's not on this computer. Run you, see what happens. Okay, you're set to 0. That's not really that bad. So that's not, okay, so it's undefined behavior. So I can't guarantee it's always going to be 0. Now here, the real fun happens when you use a reference. Okay, let's try using a reference. Or is it the reference here? I don't know. Let's do both of them. So that's still 0 there. Let's do 0 here. There we go. Okay. All right. So we panicked and attempted to zero initialize type reference I32, which is invalid. Okay. So I can't do that. The equivalent code with maybe uninit. So I can do maybe uninit zeroed. Assume init. Okay. So this does not work, but we can do let X is going to be the same reference to an I32 is equal to, it's also very unsafe. I'm going to do this maybe uninit zeroed, assume init. So assume that it's been inited by something else outside of Rust. So we're telling Rust, hey, it's okay. This is fine. Don't worry about it. Everything's good. The type of reference to I32 does not permit zero initialization. References must be non-null. However, that's just a warning. It's just a warning. It's not real. Come on. X equals, interesting. So I was kind of expecting like garbage data or something. We just get nothing. Nothing's there. Okay. So that's interesting. This is exploited by the compiler for various optimizations, such as eliding runtime checks and optimizing enum layout. Similarly, an entirely uninitialized memory may have any content, while a bool must be always true or false, hence creating an uninitialized bool is undefined behavior. So if I create you as a boolean, so you're a boolean, you become false. Okay. Now, it's just on this computer that it's running on, right? Meaning that it's unknown if it's always going to be false. It could be just something else. How about the reference to it? Yeah, still okay, still empty. I think zeroed is fine, but uninit is not. You're right. Uninit is the type reference to bool does not permit zero initialization, so it just doesn't do the thing. There's this uninitialized too. Oh, right, because I can just do the maybe uninit. Okay. Moreover, uninitializing memory is special in that it does not have to be a fixed value. Fixed meaning it won't change without being written to. Reading the same uninitialized byte multiple times can get to different results. Ooh. Well, thank you for letting me know that I can do this. Let's see if we can get different results. Wait. You only ran once. Aw. Okay, let's do an I-32 again. Will you not let me? Oh, interesting. Okay. That's just a warning. So it lets me run this, but it crashes here, but it doesn't really crash at the same time. That's interesting. Do I need to put like a double reference on this? Doesn't seem like it would work. Still the same thing. And dereference should, will that cause it to crash? No, nothing at all. Didn't even try to run that. That's interesting. Okay. So let's try without the reference. So if I do something like this, I don't know if statistically I'm gonna get something different. Yeah, they're all zeroed. Okay, I could do an uninit and then assume init. Clippy is extremely unhappy with this. Clippy is having a conniption with this. Let's run it. Interesting. Okay, so you're at 32,640 every single time here. We can try running this like a million times just to see if it's different. We can also put this as a char. Try a char too. Are you always going to be the same character? That. Huh. Okay, so if I uninitialize something and then assume that it's been initialized, that's what I get. That's interesting. Uninitialized memory is special and does not have a fixed value. Fixed meaning it won't change without being written to. Being same initially. Okay, so things can change if I start doing other things here. So if I also have like let y equals, I don't know, like like if I do something like this, maybe you write over something in that piece of memory, and then that causes weirdness here. Just to make sure you don't get compiled away. Let's debug you down here. You're exactly the same character every single time until that runs. But I could also imagine that if I like keep on doing weird things in between, then like maybe eventually I'll cause like some differences. Also, like every time I run it, I am getting something different out of here, which is fascinating, really. If I put you back, Rust Analyzer is not happy at all right now. Yeah, every time I'm running, it's getting some kind of character. It's getting a different character. I don't know what language that's from. They don't seem to be from the same languages. So like if we run this over and over and over again, eventually we're going to get English. I think. Also, the operating system is moving things around in memory constantly. That's just something that happens. So that's also like why it's like it's reading this thing in memory, but then something is going on. So if I have a slow loop, okay, let's try this. I create this character. It's definitely garbage value. That's definitely a garbage, like something sitting there in memory. Let's say I do a slow loop. So we're gonna do a loop. And then I want to debug out a reference to X. And then I want to what am I gonna do? I want to pause. So there's a sleep function. What is it? It's like thread sleep. Oh, what is it? I forget how to get there. Standard thread sleep, and then we give it a duration. Okay, so do standard thread sleep. We're gonna give this a duration. Let's do from millis. So let's do every half a second. So 500 milliseconds. If I do this, then we're going to forever read. Okay, so you're still unhappy with Clippy, but you're gonna run. Now, are you gonna change after like 10 seconds or something like that? Or are you staying the same forever during this run? It seems to be staying forever. So I guess like, did I reserve? I think Rust reserved memory. It didn't initialize it. So whatever was sitting there in memory is what I'm reading. So it's not going to be changed now, is my guess. I could still change it if I had access to this. But the operating system, I think, is not going to anymore. I'd have to run this for a really long time to like maybe verify that. But it's the reason why if I run this again, we're going to get a completely different thing. And if I update this like every 1 second, I don't think it still is going to drop it. Yeah, it's a different thing, but I think it's going to stay the same again. Reading the assembly code, it does seem like it reverses a location in the stack for the variable, even if it's not initialized. Okay, that kind of makes sense, because okay, so I'm requesting a chunk of memory that's equivalent to a character, so that's 4 bytes. And storing that away in memory, but I'm not initializing it. So whatever was sitting in there, so this value was in memory. The operating system put it in there from some other program probably. And I initialize, I run it. The operating system says, hey, nobody's using this memory. Here you go, have a chunk of memory. I then say, great, I'm just gonna read that memory. And then I go ahead and do that. Now, can I do this to keep memory and not just stack? So can I just say like a string? I cannot. Okay, so oh, look at this. Okay, we're getting what? This is now other garbage data. Okay, so maybe uninit, our X is this. We panicked at byte index 9 is not a care boundary. It is inside. Okay, so it tried to get a bunch of data, and we just got a bunch of crap. That's what we got. So it did, but when I tried to debug and actually print it out, that's when it had trouble. Or like maybe when I try to put it into a string. What if I try to put a vector in? You're a vec of U64. Okay. You closed. So we see the same thing. It did initialize it. So maybe a vec of care would be better. So here's a bunch of other random stuff that we got. Okay. The length is 31, but the index is 31. So we got too much stuff. Like that's super interesting that it limited us to 31. And then I guess if I want to control how much that I get, we're gonna do a care. Let's do 10 things. And here's 10 entries of 4 bytes. So 10 times 4, so 40 bytes worth of stuff. They should be in a row next to each other in memory, and we can see that that's happening here. It's exactly the same run to run. So it is, I think my idea is correct that it's reserving some memory, but it's not initializing. Totally makes sense. But with this way, so basically doing the same as int x in C. I think that's exactly correct. I think that's exactly correct. I think that's also the same thing as if I did something like let x here, but then it won't let me read this in Rust. But behind the scenes, it probably initializes that, and then the compiler just will refuse to compile unless I actually initialize it myself, like do something else. So let's not do the loop anymore. So it looks to me like if you wanted to write something like, what was it? It was like Heartbleed, right? That was, here, let me have X amount of memory. I want this like big, huge thing, and here's this smaller thing. Let me see all of the memory for that, and then hope that I find like a password or a username or something that allows me to hack into the system. And then eventually somebody does. I think this is a way for me to do that, because now I can get bytes out of here. I can move this up to however big I want them to do. We can do like let's do like 1,000. Oh, I can only get 31. I can only get 31 of these? No, look at this. I got way more than 31. I bet this is 1,000. This is interesting though. Oh, it's probably the print. It's the print that's happening here. Interesting. Okay. So I'd have to like convert this back to a U32 to like continue printing these. So let's debug a reference of X as a U32. I don't know if I could do that. We can do the transmute. That probably would cause more problems. I can't do, let's see. So your character, oh, right. I need to loop through this. I need to do like X dot iter for each. We get a character, and then we can debug X as a U32. There we go. I think this will work. Oh, and then don't return. Fine. Oh, I can't do a char. Apparently can't. Oh, wait, not X. The char. Okay, so this should let me do that. And then we can see all of these things that I'm getting out now. So converting them into U32s. A lot of it is zeroed out. But a lot of it is like just this garbage data that like, hey, we don't know what this is. And if it's within the realms of what we expect it to be, I can make it a character. Interesting. Very fascinating. So I would assume that if somebody's going to make some malware in Rust, they're going to do tricks like this. Just sort of like read memory and do weird things with that. Now, I can't see accessing other processes memory with this, but I can probably like mutate the memory and like add in what I want to. But yeah. So a one initialized vect is considered initialized under the current implementation. This does not constitute a stable guarantee. Because the only requirement the compiler knows about it is that the data pointer must be non-null. Creating such a vect does not cause immediate undefined behavior, but will cause undefined behavior with most safe operations, including dropping it. That would be interesting. Dropping it could be fascinating. Maybe uninit t serves to enable unsafe code to deal with uninitialized data. Yeah, so it's basically like the data here might not be uninitialized. So if I do that, but it won't let me do anything. So like this is not unsafe. We X at write. Okay. Extract the initialized data is only allowed after properly initializing X. Okay. So this is like super fascinating. Oh, I don't need to do that anymore. So let's create a function here. The function read garbage. Read garbage from memory. That's exactly what's happening here. All of you into the pool. Okay, so we have that. That's super fascinating and interesting. Let's try next, which is what was it? It was this other thing, which is we can write to it. So it's this maybe uninit. Okay, so let's do a let our x, it's going to be equal to maybe uninit, let's give it this value. So we want you to be a reference to an I32. Is that right? Then uninit. So uninit. So let's actually just allow this. So you stop yelling at us. Okay. Let's also allow the dead code. Okay, so we've safely initialized uninitialized memory. If I try to read from this, I think it's gonna not let me because it's equivalent of like an option, right? So it's essentially a none for initialized or uninitialized. So if I try to like do a debug with X here, I think it should yell at me and say, hey, this is, no, okay, this is fine. Apparently this is fine. Oh, it's the maybe uninit. So that's what I have here, is the maybe uninit itself. That makes sense. Okay. So now I want to write to it because it's the maybe uninit. So there's a write method. So I can now just say x dot write, and the value is going to be a reference to some I32 because that's what I said this is going to be. So you're going to be like 10. You need to be mutable. Then if I debug this, oh, now I can assume that it's been initted. So, maybe it would be x. X dot assume init. That is unsafe code. You return the type, right? So okay, so I'm gonna put you in there, but you're gonna return, so it's really gonna be something like x equals that, but then you're a different type now. I have to do let, don't I? Yeah, okay, so I'm doing this something. So like, this is now real x. So I'd have to shadow it, right? What do you do? Nico, hello. You have no idea what I'm doing. You're illiterate in this art. This is like, we're diving into like the deep mines of Rust here. I have no idea what I'm doing too, but it's fun. So there's that. Okay, so x.write. Yeah, okay, so look at this. They shadow x to get it back out. So that's what they're doing. So we can let x again. So x is gone with this maybe uninit. And now it's the real thing, which is this reference to an I32, and then I can debug. But now it's this 10 that is here, which is what we see when we run this. That kind of makes sense. Like, okay, we've uninitialized it, and then I manually initialized it myself. And then we can say, okay, assume in it. Zilby is crying in the other room. I am gonna go check up on him, make sure that he's okay. And then I think I might as well just go refill my water at the same time. So I am gonna be right back. He's fine. Zilby is just who's crying for to be played with. I don't know if I can get him to play. Here's a hi. Oh, okay. I'll try something like this. I'm gonna try not to make it too there you go. Nope. Oh. And now he kills the ping pong ball. I don't know if you can see that properly. He's in the other room and it's very dark in there. So I think it's too hard to see. But he does enjoy it when I throw things. Up. No. Back farther. Up. Okay. All right. I am gonna. Okay, so what are we doing? We're back to this. Okay, so it's fascinating that like we can do this. But it's mostly for FFI stuff from what I understand. And let's see. So we debug this. We've assumed init because we have initialized it. And this is us saying, I've promised that we have initialized this. If we didn't do this X right, we get garbage data when we try to write this. And that would be fine. So if I remove this, our X is now going to be, well, it's still going to be a 0, isn't it? Because maybe uninit does some interesting things. No, it's not. Here, oh, look at that. We get some random stuff here. And every time we run it, it's going to be different. So the U's are interesting. We always got 0 from that. This one, we don't. So let's come back into here. All right, so basically, this is like basically an option, right? Basically an option for it's not necessarily like a variable, but I guess it like a piece of data. It's like a piece of data in memory that may or may not be initialized as far as the compiler is concerned. So calling maybe unit. Okay, so maybe uninit. Come on. T uninit will give us will give us like some memory, right? Like give us a chunk of memory, but it won't reset that memory, won't initialize that memory for us. The compiler will not allow us to access this memory until we have called maybe uninit Well, I guess it would be the thing. It would be called assume init on the variable that we assigned on the instance of the maybe uninit. This is unsafe because the compiler isn't checking that we actually did initialize that memory. Instead, it is assuming that we did the correct thing. So this is most useful when working with FFI code. There are some, like, would it be libraries or interfaces? There are some libraries that will require a chunk of uninitialized data before, or I guess memory is right. Memory that it will initialize for us. This allows us to do that. Okay. So, yeah, this is actually kind of cool. Let's come back to here and like take out. You can use maybe uninit to implement out pointers instead of returning data from a function. Pass it a pointer to some uninitialized memory to put the result into. This can be useful when it is important for the caller to control how the memory the result is stored in gets allocated, and you want to avoid unnecessary moves. So we have this unsafe function make vector, which has this out that takes a pointer to a vector of i32s, out.write, and then we put that vector in it. So we reserve some memory, v. We then make a vector, v as mute pointer. Okay. So we call, so as mute pointer. So we give it a pointer to the place in data. Now we know v is initialized. This also makes sure the vector gets properly dropped. So v equals unsafe, then we assume initialized. So now we know it's there. Okay. I mean, that's like all very, that's interesting as mute pointer. So we can get a pointer, a raw pointer to the data. Initializing an array element by element. Okay, so let's see, we could do maybe uninit. Okay, so the vector of u32s, 1,000 of them. Now this doesn't assume init instantaneously, so we get the garbage data in there. Dropping a maybe uninit does nothing. Thus, using raw pointer assignment instead of pointer write does not cause the old uninitialized value to be dropped. Also, if there is a panic during this loop, we have a memory leak, but there is no memory safety issue. So for element in mute data, element.write. So we're writing a vector of 42 for every element. Wait, so we're writing a vector of 42 for every element? Everything is initialized. Transmute the array into the initialized type. Okay, hold on. This feels a little bit weird to me. I wanna try this one. So this is let's go ahead and allow the dead code globally. Okay. This is going to be manually initialize memory, and that's what you are. Okay, what's next? Next, we're going to be doing this thing. So we're going to create an uninitialized array of maybe. So this is initializing array element by element. Using array element by element. Okay, so inside of here, we're going to start with this like let data. And this is now going to be inside of a block. This block lasts all the way down to here. So, okay. Inside of there, we're going to have let mute data. Now, this data is not the same as this data. It's just inside of this block. So it's sort of like a function call where it's going to be dropped at the very end, and you can have like same variables inside of a variable as outside. The perhaps most obvious use case for maybe init is to allocate a buffer for reading without needing to zero it before the read. However, there are apparently some new traits on the way to allow that without maybe on init. That makes a lot of sense too. So like if I want to be as fast as machine possible, I have like, I don't know, I have a file that I want to read. I want to read stuff. I know how big the file is. So I manually initialize the amount of data for it. So I get a chunk of memory for that. And then I can go ahead and do the read operation and throw you into there and then say, okay, you've been read. I guess that makes sense. I've never run into like a performance issue with that, but I can imagine if you're working with like really huge data sets, it's possible that you could run into that problem. And this would allow you to essentially reuse data like memory over and over and over again, maybe, possibly. Exactly, maybe uninit is the main weight to eliminate the superfluous initialization of member, which is about to be overridden anyways. Yeah, and so like Rust is fast, but like this is the type of thing that you can do to make it faster. Like I guess like it's the if you tried everything and you're like, okay, it's too slow after you've written it the way that makes sense, and you're like, I need to get 10 more milliseconds. I need to get maybe like 1 millisecond. I need to get half a millisecond more out of this for one reason or another. Then this is the type of stuff you can start doing. Micro optimizations. But until then, please don't do this. Like, please don't just start with this. Wait until you do a flame graph and you find out that this is like where you need to spend your time. Basically, when you're in the domain of needing zero copy networking, yeah. So like when we do, eventually I want to do some like multiplayer stuff. When we start doing with that and we're like, okay, every nanosecond is important. And like we need to spend zero time doing stuff. We might have to play with this type of thing. Maybe. I don't know for certain that that's going to be our blockage yet. But yeah, it's always going to be like maybe. I maybe need uninit. Okay, so we have this unit data. Now this is going to be a maybe uninit. Okay, so I'm going to let I'm going to do this slightly differently here. We're going to say unsafe here, and then I'm going to do the maybe uninit. I'm going to give it the type here, which this is going to be a vector. Huh. So a vec of U32 of 1000. Oh, it's an array. Okay, hold on. Okay, I missed that first. It's an array of vec U32. That's what it was. Okay. And then you're 1000. Hi. I wish I brought some toys down here with me. I don't have any toys. I need to buy some to just store down here. Maybe I'll do that in the next week or two. Okay, so we get this, and then we can do turbofish again. Wait, is that true? Yes, then we're going to do the uninit and then assume init immediately. So this is what we got now. So that gives us our data, which it still doesn't know what this is, even though we know right here it is this thing. Okay. You are, yes, I know, you're unhappy. We're gonna make you happy. And by make you happy, I mean, we're gonna tell you to ignore all the evil things we're doing. Okay, so once we've done that, we now want to loop through this data. So let's now like rewrite this. It's gonna be inside data. This is like the raw, the uninitialized data. So I want to loop through this uninitialized data. So we're gonna do for element in mutable reference to the uninitialized data. I have to tell it do everything. So we get a slice of everything. And then we're going to element.write a vector, and we're just writing 42. Just the number 42 in there. What are you upset about? Cannot index to a value of type. Oh, so I think this is actually Rust Analyzer yelling at us. Let's continue on, but I think we have a problem here. Maybe not. So element.write Yeah, look at that. We're not getting any hints anymore. And so we're gonna write this type in. So let's do a U32, just like them. We're gonna write a vec of, here, 42 again, sure. That's great. And now everything is initialized. We want to transmute this to the uninitialized, to the initialized type. Okay, so this is when we use transmute. So transmute from something to this thing and pass it in this data. And then we're returning that into this data. So now we're going to transmute. Okay. So now we're going to standard mem transmute. I think it can do, okay, we're going to take in this uninitialized data and we're returning into this data. Oh, it doesn't know what you need to be. So you need to be what? You're gonna be a type of vec. No, you're an array with a vec of U32 1000. It's unsafe. Oh, I need to do another unsafe here. And I return this. You're still super unhappy. But now I have this data. Let's not do 1,000. Let's do like 10. And then down here, I should be able to debug now. Data. Let's see if this runs. It does not. Okay. So it's not Rust Analyzer. That's actually the full compiler is unable to figure out what this is. Oh, okay. So you can't. It's interesting. Rust Analyzer can't. Oh, it's unknown. That's why. Okay. So I need to tell you. Oh, wait. Did I do this wrong? I did that totally wrong. I put a semicolon on it. Okay, so now I element the right. What are you upset about? No method name right for mutable. I mean, assuming it does give me back that thing, doesn't it? Hold on. What did I do wrong? So we say that you're this array. Oh, so I'm not giving it like an array of something. It's basically just that here's just a piece of data and memory and it's uninitialized. So I need to do the same thing here. So at this point, this is completely useless. That's not helping me. If I'm gonna have to do it here, I might as well just do it in one place. So you are gonna be this array of maybe uninit of with a vec of U32 inside. And you're 10 items. There we go. Now you're happy. So now we see that that's a maybe uninit. And now we see, okay, I have now put everything in there that it needs to be. So can I do this with more things? Like basically I can replace this, like it's a vector right now, but I can put whatever I want in there. I can put, I don't have to put a vector. I could put anything. Let's say I want you to be just U32, in which case this becomes 42 like that. What else? Oh, you need to be just U32 here. And you should be exactly the same, except instead of a vector of things, it's now just the 42. Perfect. So yeah, that's an interesting way of doing stuff. Okay. You could also work with partially initialized arrays, which could be found in low-level data structures. Create an uninitialized array of maybe uninit. The assume init is safe because the type we are claiming to have initialized here is a bunch of maybe uninits, which do not require initialization. So we're doing exactly the same thing. We have an array of maybe uninits. So that's sort of like an array of options, but for like deep down memory stuff. And inside of them, we're gonna hold strings. So we're gonna have unsafe code to get this. So we just assume init. Okay, so now we have uninitialized data. Count the number of elements we have assigned, so we have 0. We're going to go through 500 of them and write hello. For each item in the array, drop if we allocated it. Okay, so we just do a drop in place, which, have we written down that yet? I think we have. Yeah, we're gonna be looking at that shortly. And then the pointer for it. I mean, interesting things, but like very, very similar to this. We just do part of it. Initializing a struct field by field. You can use maybe uninit t and standard pointer address and mute macro to initialize structs field by field. Okay, so this might be more interesting. So we have this struct foo with a name and a list. So we create our uninitialized data, which is going to be an uninit that holds this foo. We get a pointer, so we get the azimuth pointer, so we can start writing to it. Using write instead of assigning via equals to not call drop on the old uninitialized value. Right, so we're just overwriting like into that piece of data. Initializing the list field, okay. If there is a panic here, okay, so if we cause a panic, then the string in the name leaks. So this allows us to sort of create something over time. And it allows us to do this without having a oh, what is it called? Without having options. So we've actually run into this problem a few times. When I was trying to build constructors for like complex objects in like a game, let's say. So let's do this wouldn't be necessarily a function. This would be potentially a full struct. So let's say we have like the struct of a, let's see, what would it be? We could do this as like an entity. As a game entity, or let's do the location again. So if I do struct location, an X and a Y. So great. You both need to be filled out to be correct. But if for some reason I can't do that all at once, and I need to instead use a builder. So we're gonna do another one. So we're gonna do a struct location builder. Now inside of here, I think I need to store this maybe uninit. So it's gonna be our sort of like location under construction. So the location is gonna be a maybe uninit with a location inside. So then we're gonna have an impl location builder. So pub function new, and we're gonna return a self, probably own self, and then we need to set up with that maybe init, which I think we can. We're gonna do a self location. Okay, so this is gonna be our maybe init. I think I have to do this as unsafe too. Uninit. Assume init. Like that. So you need to be unsafe. Expected a comma. Oh, I think it's a dot, right? Okay, there we go. So I've now created this. It's unsafe. So the way I'm going to use this, function plain with a constructor, with a builder. So we're gonna say let, I guess like normally in a builder, you don't do like let into a variable. You do let with like dots for like calling different functions for this. So we're gonna say like let our location is gonna be equal to a location builder new. So far that gives us this location builder. Okay, you're unhappy so far. Then I want functions in here. The pub function, so to set the X, right? So like X, we're gonna have a mutable reference to self, and then whatever the X is gonna be, which is gonna be a F32 in this case. And I'm gonna return probably a new self. So let's actually just take ownership of self. Okay, so we're gonna return self, and we're gonna say self.location dot x dot right. No, what was it? It was right. How do they do it again? Oh, they got a pointer, right? So asme pointer. Okay, that's what it was. So we have to get the pointer first. So we get the pointer, and then we can do we use this address mute macro to then write that down. That's fascinating. Okay, so we're gonna get a pointer to this. So in here, let's start over with this. So let our pointer is going to be equal to self dot location dot as mute pointer. Okay. Then I can get the address of the mute. So this is going to be an unsafe too. So unsafe, I'm going to get the adder of mute. I kind of want to add this now. This feels super sketchy, but like you said, we're in standard mem, so things should be sketchy. Dang straight, yeah, absolutely. Okay, so address and mute. Now, this macro creates a mutable raw pointer to a place without creating an intermediate reference. So this takes in this, okay, so we now dereference our pointer in here, but then we can get the X out of it, which is going to be this thing. So we get that, and we get the address, the memory address of that, and then we can write into it what this X is. And that's it. Okay, cool. Then we return self. So now we have a partially filled out. So, okay, great. Now I want to do the same thing for the Y. So now we're going to have a Y that takes in the Y here. It's an F32. We do the same pointer. We replace the Y and we write in with this Y. Now, then once it's all done, I want to return, like build it back out. So that's going to be like a pub function build. In which case, I think it's done now, so we can just pass in the location. Now we assume init. Can I just say that you're just a location now? Would that work? No. The asmute pointer needs to be that maybe uninit. Then that works. We can get the asmute pointer. Okay. So if I build and we take in a self, and I want to return a location, then at this point, you think the assume init? Yeah, I'm wondering if this assume init isn't necessary then, which that means the unsafe isn't necessary. Although it's not yelling at me about that yet. Oh, because of this. So then I want to do self dot location dot. Oh, now we can assume init. Now we assume init. Which means you are unsafe here. Okay. You don't need to be unsafe because just getting an uninitialized thing isn't inherently unsafe on its own. It's this assume init, and it's all these pointers where I'm doing this address mute and the write. That's what's unsafe. Okay. Oh, you know what? The command to do that, and because I'm in code spaces, I haven't set that up here. Like I could, I need to reset that up. I don't have that on there. That's a good point though. It's like it's gone back up and down on me too. Like where it sometimes works and sometimes doesn't work. But if I do like search for Twitch highlight, I'll install it. But I need to actually get like my code and do all that stuff. I'll have to do that off stream. I don't want to expose my key again. So this is gonna work here. So if we make you derive debug, then we'll go ahead and debug our location. And playing with builder will throw you into main. Oh, the location builder. Oh, wait, I'm doing this wrong. Okay, so we're doing new dot x is like 10.0 dot y is 20.0 dot build. Okay, so then this should work. This should work exactly as we expect it to, and we should be able to see. We should see that location printed out. Perfect. Now, I have no protections here. If I attempt to assume init and I forgot to do the x and I just put in the y, we should get garbage data or a 0, I think is what we've learned with the at 32. I think we're gonna get garbage data for the x. So we get the, okay, not a number. So it's garbage data. It turns out to be not a number. Okay, perfect. So how do I protect myself from this? If I'm gonna do that, then I need to know probably like a Boolean in the builder. So like, we need to know if it's like been all set, which is one of those things where it's like, well, if I need to know it's all set, then I might as well just like mirror what this is with like options, which is what I see a lot of people in builders do, is like an option for X, an option for Y, and then the build is just extract the options and put this through. Run this through Miri. What's Miri? Or wait, the Miri thing? What was that? The convert it to like the transmute thing? So this is it, like, I don't know. It doesn't, it feels like it's not really that useful for what I'm doing right this second, like for this. Oh, if I have Miri installed, cargo plus nightly Miri run. Oh, let's find out if I have it installed. Oh, I don't think I have nightly installed. Let's see. Oh, it can test for undefined behavior. Oh, okay. So rest up. It's like install nightly, right? Okay. Oh, then I need to do rest up component add Miri. Tool chain. Can I just do nightly? Yes. I will run. Okay. Cargo install XX Zargo to install a recent enough Zargo. Oh, okay. I think you run Miri in the Rust Playground website. Oh, wait. Well, here. What's the worst thing that happened? I'm on a VM. I don't care. I can destroy this VM and create a new one easily.
Einhorn is a man.
And this way I get a nice auto completion, which is why I'm doing it here instead of all this stuff in the playground. Okay. Sure.
Finkel is Einhorn.
Okay, so it's a binary target must be available for cargo run. Okay, so hold on. We have to do run example, maybe uninit. Okay. So here's our stuff. Okay, so undefined behavior using uninitialized data, but this operation requires initialized memory. So line, okay, so let's sign if bits. So wait, in float. Ah, okay. This indicates a bug in a program. It performed an invalid operation and caused undefined behavior. Okay. But that's just because I'm doing... Interesting. So yes, I do have undefined behavior. You think it errored in a debug impl. Oh, so let's oh, also I'm not saved here for some reason. Let's not derive debug, which means I think what I could do is I could do a can I impl debug myself? Oh wait, it's... Oh, come on, do the right one. Standard format debug. Okay, so I want to do this. We're gonna do the, actually, you kind of figured out what I want to do already. Now, will you be better? Still the same thing. So it's like it's initializing. Oh, I guess maybe even the display is not. Yeah, because okay, so what Miri is discovering here is that it's possible for me to do this. What if, because the compiler doesn't know that I'm doing this like correctly here. The compiler just knows that there's a possibility that I might do it incorrectly. So what if I were to do location builder new, semicolon like this, we make you mutable, then I debug location, and then I also do location. I do this again. It's like let location equals location, and then the rest of this, and then I debug you again. You are upset because it doesn't implement standard format debug. So like it doesn't matter the fact that I did this here. The fact that I have this derived debug or attempting to display at all is like potentially bad juju. And this is location builder is upset. Can I do this? Use of move value. Oh, right. I don't want to like actually take you away. It does not need to be mutable. Okay, fine. Be that way. All right, so we give ownership, we do all that stuff. Everything is great. We'll run you again, and we should get the exact same errors because like, hey, that's what it's protecting me from. It's saying, hey, what if I do that? Ted, hello, welcome, and thank you so much for the subscription. You've been subscribed for 6 months. Still live so late. I know my Sunday streams are my late streams. I think it's detecting that you're not initializing X. Try to initialize it as well. Oh, you might be right. I forgot that I removed that. Let's do that. Either way, let's see. Maybe not either way. Oh, yeah, because this is perfectly fine. That's okay. That's interesting. So Miri does help you prevent from problems like. So like I have all this unsafe code, and it's not just going to yell at me. It's going to say like, "Hey, I'm not doing something evil." So that's pretty cool. That's a nice way of like detecting whether or not you're causing weird issues. That could be something to throw into a like a CI/CD system. Especially if it's like an open source project, we can say, look, let's just make sure we're not going to do anything bad. We're going to do good. We're going to do good here. Now, if I put you as public, you know, it's because I want to do evil things. I want to say, I want location dot location. This should fail Miri, right? Because I have not, it's uninitialized data. No. Because it's still the maybe uninit. It's still the maybe uninit. It's it doesn't detect all undefined behavior, but it covers a lot of cases. It certainly covers more than just Clippy would, which is nice. That is super nice. Okay, so how would I potentially do this? I would have to, yeah, so like if I tried to build off of this here, that's where it's gonna detect undefined behavior. Since Miri is a runtime analyzer, it only detects errors when you actually do something bad. That's a good point. So, this is a different way of doing a constructor, like a builder pattern for this. I'm trying to think, like, would this be useful in like an ECS system? Like, for example, I want to build like my own database. I want to put it all in memory. I want to sort of like start uninitializing data. Like, I guess in some ways, maybe yes. Like, I want to initialize all these things, and I don't want it to take the time to initialize 1,000 vectors. So I maybe like tell it that I want 1,000 worth of space, but I don't want to like actually go through and do the work of it just in case I don't use it. No, that still doesn't make sense. Because if I'm not going to use it, then don't make it at all. Then don't request that data. Let's see. Now, okay. Miri should be okay then. Let's say I don't debug everything. Let's make these both public. If I want to do just a publication.y, and we're still gonna not put the X in. If I do this, Miri should still be okay with me, right? It is. Okay. So one of the things that I was thinking of before for an ECS system, like we've talked about like the different ways of like storing the data for this. If we have like an entity, so like previous, like we've done it 2 different times. We've had dynamic dispatch with any, and we have had an enum. So the way the enum worked was like enum, like entity data, and then we could say like, okay, you can be an F32, which holds an F32. You could be like a GGEZ, what is that? A GGEZ mesh. Which then held a mesh inside. But the problem here is that if I create this, the F32 is going to take up the same space as a mesh, which is much, much larger of a thing in memory. So something nicer to do would be a struct. So a struct entity data would then potentially hold one of many things. So we probably have like a type field for entity data type, which would then have to be an enum. And then here we can have like an F32, a GGEZ mesh, things like that. So you're going to be the type here. And then we're just going to have the actual thing that we're storing, right? So that would be like the F. I guess you'd be like the F32, which would then hold an F32. A GGEZ mesh, which would hold, and a GGEZ mesh. Let's like store something else that like makes that we actually have the type here. So maybe like a U32. Maybe U64. So it's different sizes. So this would be a U64. But when creating this, I don't like, how do I know which one to create? I'm gonna have to use like, I don't want it to actually initialize all this data for each one of these. So I probably want to not store the F32. I want the maybe uninit with an F32 inside. Maybe uninit with the U64 inside. I guess I have to do something like my type. So then when I create this, the constructor is probably going to construct each of these. So impl entity data. We're going to say self. This is not going to be unsafe. So we need like the type. Actually, we don't need the type at this point in time, do we? We just have to say like you're unknown at this point. So my type is going to be entity data type unknown. But this F32 is going to be a maybe unit new. No, not new. Uninit. And the F64 no, the U64 is going to be a maybe uninit also. So if I do that now, I have all this uninitialized memory for each one of these things. But okay, and does that still make sense? Does it still make sense? Because when I run this, is it still going to take up all that data? It's going to initialize all that data, but if I never use the U64, when I compile for production mode, it's going to remove all the stuff for it and not even do the initialization? Is that true? Do any of you know like how production would work for this? If I don't use this U64, maybe uninit will still take up space. Okay. I was really hoping it would compile away. So this won't work. It's still going to take up the full U64 worth of space. So I don't think this works. Yeah, okay. This is not gonna work for me. It's an interesting idea, but I think we have to stay with the same FFI use for it, or doing crazy builder patterns with it to like avoid you. This is basically a lot of work to avoid using option. That's all I'm doing, avoiding using option. Okay, let's go back to this. What do we got here? Any more cool things? Maybe uninit is guaranteed to have same size, alignment, and ABI as T. Is that because it implements borrow? However, remember that a type containing, or no, wait, it's not borrow, it's borrow or ref. Like both of those do the same thing. Like as in, you get the reference of it, you borrow it, and you get the thing inside of it, and then it implements the same structures, the same methods, the same properties. Like you can't tell from using it. However, remember that a type containing a maybe uninit is not necessarily the same layout. Rest does not in general guarantee that the fields of a foo T have the same order as a foo U, even if T and U have the same size and alignment. Furthermore, because any bit value is valid for a maybe uninit T, the compiler can't apply non-zero niche filling optimizations, potentially resulting in a larger size. Okay, so a size of an option bool is 1. A size of an option maybe uninit bool is a size 2. If T is FFI safe, then so is maybe uninit, which is I think one of the biggest things like to use it with is FFI safe. While maybe uninit is repr transparent, indicating it guarantees the same size alignment in ABI as T. This does not change any of the previous caveats. Okay, so they may have different sizes. Okay. Maybe uninit is a union type, and the repr transparent on unions is unstable. Over time, the exact guarantees of repr transparent on unions may evolve, and maybe uninit may or may not remain. Okay, so basically there's just a lot of caveats to using it. All right, so let's take a look at our implementations. So we have new, we have uninit, uninit array, that's nightly, so we're not going to look at it right now. Zeroed, there's this right, as pointer, as mute pointer, okay, assume init, which this is that one of those unsafe ones. Assume init read. Interesting. It'll be nice when that becomes like normal. We'll take a look at it. Assume init drop. Okay, assume init ref. It's also unsafe. And then assume init mute. Lots of nightly only things on this. Okay, and then our trait implementations. So let's okay, so new is pretty simple, although like we never needed to use new. We just did uninit. So what does new actually give us? It gives us a maybe uninit t. Oh, we give it a value. Creates a new maybe uninit initialized with the given value. It is safe to call assume init on the return value of this function. Note that dropping a maybe uninit t will never call t's drop code. It is your responsibility to make sure it gets dropped if it got initialized. That's interesting. So it won't, when it drops, it doesn't call the drop code. So initialize data with provided value. I guess initialize memory with provided value. and safely run assume init, but then won't run the drop. So that, yep, don't look at that. You don't need to look at that. Okay, so doesn't need to run drop. Interesting. Okay, so let's have this struct. Let's implement drop in here again. So impl drop for location. And all we're gonna do is we're just gonna do a quick debug for location is dropped. Oh wait, can't do that. Create the function first. So then we can just do we have a debug here. So we'll debug I am dropped followed by self. So if I do another function in here, function, this is using new. Okay, so we're just basically gonna initialize this and set this up ourselves. So we're gonna do let our maybe location, maybe initialize location. It's gonna be equal to a maybe init new, and then we're gonna pass it this location with a x of 10 and a y of 20. We can safely call dot assume init on this. No, I can't. I guess we still have to use unsafe to call that, because it's an unsafe function. It won't determine that. Okay, so let location is equal to unsafe maybe dot assume init. Okay, and I can debug the location here. But as this function ends, it's not going to run the drop. I think that's what it said. It won't run the drop now. Or maybe that's only if this goes out and we don't do this thing. I don't know. Let's find out. No, okay, so we ran the drop here, but I did do the assume init. So if I don't do the assume init and I just debug the maybe initialized location here, I debug that out, it drops, and then that's not going to run the drop of the location. Is that? I think that's what it was trying to say. That's true. Okay, so I debug out this. I can see that, hey, we're storing this location inside there, but drop does not happen. So this would cause the location drop to run when function is completed. Ah, wrong one. Okay, so JavaScript, you're Rust. Okay, so that gives us that. On init, we've already sort of seen us use this. which is this is going to be request. So like get a chunk of memory from the, I guess like the kernel or operating system. So let's just say operating system to be like maybe the safest with this. So get a chunk of memory from the operating system, but don't initialize it. It can have whatever the OS had put in it before we got it. It is possible to print out this garbage data if we assume in it. Zeroed. So creates a new, maybe in an uninitialized state with memory being filled with 0 bytes. It depends upon T whether or not that already makes for proper initialization. For example, usize is initialized, but like a static i32 is not, because references must not be null. Okay, so initialize, so get a chunk of memory from the OS and attempt to fill it with 0 bytes. Sometimes, like depending upon the type, this will initialize or not the chunk of data. It's like the data. So the example is like a U32. So a U32 will be initialized properly with a 0, but an I32, a reference to an I32. But then we also found out like a character and other things will not be. Or like a vector also, like a vec of really anything will not be, and we will still get garbage data. Okay, right. So sets the value of the contained item. So set the value of the contained item inside the what is it? The maybe uninit. As the content is stored inside, the structure is not run for the inner data. Right, because we're just replacing it in memory. The other thing is that the sizes must be the same. Interesting. Okay, this also returns a safely initialized. Okay. So returns the now safely initialized data for stored in the maybe uninit. Turns a mutable reference. So that's interesting. We used write, but we didn't try to get anything back from it. But that's interesting for it. Okay, as pointer. Now this gives us a const t, which is, I think we can do some really interesting things to it. But reading of this pointer or turning it into a reference is undefined behavior unless maybe undernet t is initialized. Writing to memory this pointer points to is undefined behavior, except inside of an unsafe cell. And we've seen unsafe cell before to do that kind of thing. So we could probably use this combined with unsafe cell to do interesting things. So as pointer, get a const t pointer. So we can like do whatever we want to with it. Now correct usage of this. We get this as pointer out after we've written to it. So, of the contained data, it's best to use this after after initializing the data. Data, for example, with a write. We didn't do that one necessarily. I think some of the more interesting ones are I think we did as mute pointer. That's what we did, which gives us this star mute t. And that was cool because here we can see f of the location. Yeah, we did the as mute pointer, which gives us this star mute location, which then allows us to get this entire thing to sort of initialize that data one at a time. So that's exactly what we're going to do in this next section. So this is get a star mute t pointer to the contained data. This can be used to initialize the data or parts of the data. And then we'll give like an example of that. I think the address of mute is what's unsafe there. Okay, assume init. So this like tells the compiler that the data has been initialized. Potentially like either manually or outside of Rust, and that it is now safe to use. Like now safe to use normally. This is unsafe because if we are supposed to manually initialize the data and don't, then we are causing undefined behavior and will probably get garbage or cause a / cause a crash. So we did some of that here. It's here. Read garbage from memory. Oh yeah, both these actually work. Okay, assume init ref. We didn't do that one. It's a shared reference to the contained value. This can be useful when we want to access a maybe uninit that has been initialized but don't have ownership of the maybe uninit, preventing the use of assume init. Okay, so basically it's the exact same thing. So the same thing as assume init, but allows us to get access to the contained data without owning it. Without owning it or taking ownership of it. That's actually kind of nice. And you are y'all red because danger. Assume init mute. So that must be the same thing, but we have mutable access to it. Yeah, so same thing as assume init, but allows us to get access to the contained data without owning it or taking ownership of it. And really this is like allowed us to get just sort of like ref access to it. And this one is like that. And that's it. That is maybe uninit, which is pretty cool. I like we did a constructor pattern, like a builder pattern that uses this without options. But I don't know how I would put safety checks into that. We'd have to like read into those things to see if they've been set. And that's not, I don't know like how useful that really is. It's interesting though, like that we could do that. But the undefined behavior is not the greatest. But I wonder if we can throw, there was it a function? I can't remember what it was that allows us to try, and I don't see that anymore. It's not. I think it's a constant. It's not a macro. Was it a struct? Not any of those things. Okay, so I don't. I forgot where that was. I don't think we can. Yeah, I don't have it written down in here. What was it? It was the we did write something down in here, but I don't think I have Oh, I don't know if I could find it. What's a keyword for it? Did I put like catch in there? No. No, I did. What? No. Hold on. Catch. There's this panic unwind safe. That's what it is. So if you panic when I do that, can I catch you? I wanna try that out. So let's using this playing with the builder here. If I try to access the X, I guess that's just gonna work. That's the problem, is it's just gonna work. It doesn't panic. That's our situation. Assume init doesn't check. It just assumes, which is, well, unsafe. So yeah, no, that's not gonna work. Like the same thing stands. It just don't call it unless it's been initted, and you know for certain it's been initted. And there's no way, like, this has not been 100% initted. There's nothing stopping me from doing it, but it will do it. And I don't know a better way to like track that manually, besides writing a bunch of code in which an option would have been made it so much easier and nicer in the end. So I'm just gonna say, there we go. Maybe uninit is done. We've got that done. Now it's 12:10. I think the next thing we're gonna do is this drop in place, but my throat's starting to like feel it. I do so much talking during the day at work too, so I think I need to go take a break, eat some lunch, go do the rest of my day type thing. So I'm sorry, I'm gonna have to end the stream at this point in time. What I want to do is I want to set up. Let's see, do we have anybody we can raid? Is there anybody that I'm following? Hirose is online doing a Vim-like text editor. TBD Gamer is online. Any raid targets you all suggest? You're gonna go take a look at TBD Gamer. Is Handmade Hero online? Oh, Handmade Hero is online. Yeah, let's do that. That's a good idea, Chantilly. If you've never watched Handmade Hero, Handmade Hero has been building a game from scratch for, I don't know, years. Oh wait, no, he's doing Sleep now. Sleep Made Hero? Wait, what? Hold on, let's I think he just went offline. So I can't hear anything. So let's see. Well, okay, maybe it just crashed.
No, I cannot do a stream like that because I don't know. I don't really do much graphics programming.
Okay, that's a bit odd for right now. I don't think he's doing any coding right now. He might be doing the Q&A section of it, which is usually at the end after he does the coding part. So I'm gonna skip that for right now. Let's do TBD Gamer. TBD Gamer.
Stream well, a little frustrating as I could figure out how to get the Twitch pod to work. I hear you. So I was going to start the stream earlier today. However, I actually I was trying to get the bot into Docker, which was what I was doing last stream.
All right, looks like just some application mobile friendly and C3 Blazor. I've never used with those. I don't know how much I'm going to be able to hang out with you all because I need to go have lunch. You know, one of those things, food of some kind. So let's go ahead and set up a raid for that. Raid for gamer and start that. And I am going to switch over to ending. Thank you everybody for hanging out with me today. It was a lot of fun going through all these sort of like unsafe things in Rust. It's been cool to sort of like see what we could do, get some garbage data out of memory, and do all that kind of stuff. Anyways, I am not streaming during the weekdays, no schedule. Sometimes I stream in the after work times, so like after 6:30 p.m. Mountain Time. I'm usually playing a game during that time or doing something like sort of chill. We're doing this type of deep dive on Sundays. So if you only want to see that again, I'll see you next week, Sunday at 8 a.m. Mountain Time. All right, with that, have a great day and see you next time. Bye.
I have to wait a second just to make sure. You never know who's getting ads. That's a problem with Twitch. Hello. Thank you very much for the raid. I appreciate it. It's a great start. I just brought the stream up. Hello to all those that have joined. Give it a slight pause. So today's stream, the focus is I've been developing this application. Chantilly Kate, thank you. Hello, welcome.